Hello.
Good morning, afternoon, or night. We are Bea, Jesus, and I, Liher, and we are going to speak briefly about the design principles of the biochemical oscillators. First, we will explain what a biochemical oscillator is and which are the main oscillatory motifs, and then we are going to talk about the requirements for those to take place.
Chemical oscillations
Are ubiquitous and vital phenomena in living systems. From the most basic singular cellular bacteria to the most sophisticated organisms, periodicities have been observed in a broad spectrum of biological processes, among others, heartbeat, circadian rhythms, DNA synthesis, or cell division related processes such as mitosis and meiosis. Defects on these oscillators can cause many diseases from insomnia to even cancer. Elucidating their fundamental mechanisms is important, but it's at the same time challenging due to the complexity and diversity of these oscillators. As I said, these oscillators perform several functions in general, but most oscillators function as endogenous pacemaker. Circadian rhythms, for example, exist in almost all organisms on Earth and help them to adapt to the natural periodicity of the day-night alterations. We will study the conditions to these oscillations to be produced, such as negative feedback, time delay, and nonlinear kinetic rate. Oscillators have systems-level characteristics that transcend to the properties of individual molecules or reaction partners, and they involve the full topology of the reaction network. For that, we will analyze some properties of the oscillatory systems, such as periodicity and robustness, from the theoretical and the numerical point of view. We will study these requirements by starting from the simplest condition and including step-by-step remaining ones.
It's Beatriz. First of all, we will only consider negative feedback, a highly idealized model of periodic protein synthesis, whose production represses the transcription of its own gene, as shown in schemes 1 and 2. Equation 1 shows the time rate change of protein concentration. The first term is the rate of protein synthesis, and the second is its rate of degradation. The synthesis term is proportional to 1. The signal S, which could be, for example, the concentration of a transcription factor that upregulates the gene, 2. To a factor that represents how gene transcription is downregulated by protein Y, as said before, and finally 3. To the dissociation constant for Y binding, K sub D. On the other hand, the term related to protein degradation is proportional to 1. The rate of synthesis of Y, K sub 1, 2. The concentration of protease E that degrades Y, E sub T, 3. The turnover rate, K sub 2, and 4. The Michaelis constant, K sub N. We plot these rates. Both authors in Figure 1 and our results in Figure 2 are shown, as we will be doing with all following plots. We can see that, given that at the left of the equilibrium point the green line is above the red one, somehow production wins degradation, and the opposite happens at the right side of the equilibrium point. So it can be seen that the protein concentration will be drawn towards a steady state value, which is Y sub 0, without any oscillations. But this is not what we want, since we are looking for oscillations. To try to solve that, in the next step, we will consider explicit time delay by means of supposing that the rate of protein synthesis at present time, t, depends on the past, t minus tau, being tau, for example, the time delay required for transcription and translation. Now, our kinetic equation becomes equation 2, and for proper choices of rate constants, its solution shows periodic oscillations, as shown in figures 3 and 4, in which we can see how time delay causes the negative feedback to overshoot and undershoot the steady state. In explanation for proper choices, we mean that S, P, K sub M, and tau must satisfy some constraints, such as 1. The time delay must be sufficient, 2. Reaction laws have to be nonlinear, and 3. The rates of opposite process must be balanced. We get all this by following authors' indications and calculations in the supplementary information of the paper. After some of these calculations, the last requirement can be summarized, imposing that for a fixed value of P and KD divided by M, The curve for time delay versus signal must be above given curves in figures 5a and 5b. In explanation for that, we mean that for one of these curves, for example the one with p equals 2 and kd divided by km equals 10, the time delay has to be greater than approximately 2.5 and signal greater than approximately 1.2. Only then we will observe sustained oscillations as shown in figures 4 and 6, in which we plot time delayed rate of protein synthesis as a function of the present protein concentration yt. Nevertheless, we could not reproduce the simulation in figure 6. We believe we couldn't because of the other solver 4 equations with time delay we used and the initial conditions provided by the author for these simulations that weren't as clear as we would have desired. Additionally, we tried them some values of time delay tau for p equals 2 and kd divided by km equals 10 in figure 7 to see when oscillations are present or not. As expected, oscillations between tau equals 2 and 4, which is the limit, begin to exist. Over this value, for example 8 and 10, sustained oscillations are shown. Below tau equals 2, the chosen point was 0.5, oscillations didn't even exist. Finally, some long and non-trivial calculations that involve the units of the axis in the figures can be performed to obtain, for example, the period of oscillations in protein synthesis and degradation processes, knowing that the estimated time for transcription and translation is roughly about 20 minutes, but we won't dig into it. Till now, we have seen how negative feedback, nonlinearity, time delay, and time scale constraints are generally needed for all biochemical oscillators. In the following model, we will try to avoid including the time delay in the kinetic equation by including mRNA and its dynamics as an intermediate in the process. The kinetic equations are now equations 3 and 4, being k sub dx and k sub asy the rate constants for degradation of mRNA and synthesis of protein. X and Y nucleins are shown in red and green in figures 8 and 9. Along the x nuclein, the derivative of x with respect to time is 0, which means that there is no change in x direction, so trajectories move horizontally in the xy plane, because there can exist change in y direction. The opposite happens in the y nuclein. Taking into account where the red line values are greater than the green ones, we can plot the black arrows that indicate the direction of motion of trajectories as they cross the nucleins. In nucleus intersection, we can have a steady state since there is no variation. It means that both derivatives are 0. The shoot curves are the solutions of the system of differential coupled equations 3 and 4. We can see how every trajectory spirals into the stable steady state located in the orange circle. But although we can observe some oscillations on the way to the steady state, sustained oscillations in this simple system are impossible as shown in figure 10. But before forgetting the idea of replacing the time delay by a series of intermediates, let's include differences between nucleus and cytoplasm, which actually happens in some eukaryotes. We do that by expanding equations 3 and 4 into equations 5. If we plot the solutions in figures 11 and 12, we can observe our desired oscillations. The constraints for oscillations to be produced can be summarized in figures 13a and b. Figure 13a shows, as seen before, that for the negative feedback loop to oscillate, P and Kd divided by Km must be large enough. We didn't dig deep into figure 13b, but it represents the time scale balancing needed between nucleus and cytoplasm processes, in which can be seen that the half-lives of mRNA in the nucleus and protein in cytoplasm must be properly balanced. For both 13a and 13b, the parameters must be in the shaded region of the diagram. From results in figure 13b, it is remarkable that it can be also deduced that oscillations without time delay can only appear for 3 or more component systems. To explain that, imagine a 4-component system. If any half-life becomes very short, then that component maintains its steady state value and the feedback loop reduces to 3-component and remaining components oscillations persist. It wouldn't happen in a 2-component system that could be reduced to a one-component system and oscillations would disappear. It can be then deduced that the limit for oscillations without time delay is a three-component system. Finally, it is interesting to say that this mechanism has been chosen for modeling circadian rhythms in flies and mammals, governed by the PRR protein which migrates from cytoplasm to nucleus to block expression of the PER gene.
Hi, it's Jesus. Now we are going to see how time delay by positive feedback can create oscillations. Let's assume that protein Y can also bind to an allosteric site on protease E and inhibit its activity as shown in scheme 3. This system is described by equation 6, where we have two new constants: the rate constant for an alternative pathway of protein degradation and a constant that characterizes the strength of the inhibition of enzyme E by its substrate. In figure 14a and b, we draw the north lines of equation 6. The effect of positive feedback is a kink in the degradation curve, displayed in red, and the kink forces the dynamical system to overshoot and undershoot the steady state repeatedly, performing oscillations as we can see in figure 14c and d. But the value of the signal S and the inhibition constant Ki must be properly tuned for oscillation to occur. As we can see in figure 15, the signal strength must lie within strict bands. S must not be too large or too small, and these oscillations require positive feedback given by constant Ki. They disappear if Ki is too small or too large. As we can see in figure 15b, c, e, and f, if S of Ki values are too high, oscillations are damped and a steady state arises. Now let's move on to three-component regulatory motifs with 4 interaction links, which can be classified in these 3 classes. Class 1 are the delayed negative feedback loops, which are formed by 3 or more components connected in a single loop by positive and negative links, with an odd number of inhibitory links. When we plot x versus y, as in figure 16a, the limit cycle trajectory, curve 3, does not cross curve 1 in a horizontal direction because the rate of synthesis of x depends on the concentration of y sometime in the past. If we are plotting x versus z, as in figure 16b, the limit cycle trajectory does not cross curve 2 in a vertical direction because the rate of synthesis of Z depends on the concentration of X sometime in the past. A biological example of this type of loops can be found in the oscillations of the p53 protein in response to ionizing radiation, where X is p53, Y is MDM2 mRNA, and Z is MDM2 protein. Class 2 are the negative feedback loops amplified by a positive feedback loop. Depending on where is located the positive feedback loop, we can distinguish between activator amplification as in figure 17a or inhibitor amplification as in figure 17b. In the case of activator amplification, the X-0 line is kinked by the positive feedback loop, acquiring a Z-like shape. For the inhibitor amplification, the Y-0 line is kinked, adopting an N-like shape. In either case, trajectories are now forced to wheel around the steady state onto a closed orbit as shown in curve 3. An example of activator amplified negative feedback loop is the model of mitosis promoting factor MPF in frog egg extracts, in which W is CDC25, X is MPF, and Y is CDC20. An inhibitor amplified negative feedback loop has been used to model endoreplication, which is periodic DNA synthesis in the absence of cell division, in which X is CDC10, Y is CIG2, and Z is RUM1. Finally, the class 3 oscillators are the incoherently amplified negative feedback loops. They are incorrectly because in these cases X is regulated simultaneously by a positive and a negative feedback loop. The negative feedback loop can oscillate in its own right, but the additional positive feedback loop adds stability and robustness. The positive feedback loop may be composed by two inhibitory interactions, as in scheme 4, or by two activatory interactions, as in scheme 5. Some examples of this kind of oscillatory networks may be found in the glycolytic oscillation, cyclic AMP oscillations, and in cell cycle transitions.
Finally, after explaining the different possible oscillatory motifs with 3 components and 4 links, I would like to address more complex topologies and oscillatory behaviors. These chaotic oscillators are the result of the combination of 2 or more oscillatory motifs. By combining oscillatory motifs in a common mechanism, we can get exotic behaviors as the one shown in the figure of the right, adapted from Rosler classic paper. This chaotic oscillator is the result of overlapping 2 activator amplification oscillations with 2 negative feedback loops and sharing a common activator. On the right of that scheme, we can see the representation of the chaotic trajectory of this mechanism. Even though along the time course X fluctuates up and down, it never repeats. Also, if we represent this in a three-dimensional projection of the chaotic trajectory as shown below, we see that the curve never closes itself. So, we can conclude that these mechanisms are not periodic. Summing up, even though the requirements for chaos are not clear, we can conclude that these behaviors arise in systems of coupled oscillations. These multiple coupled oscillators seem to be common in complex radiation networks like those in cell physiology. But it's surprising that these kind of features are not that common as suspected. Maybe because within large populations of cells, the chaotic trajectories of individual cells are averaged. Also, in experimental data, when the behavior of single cells are monitored with fluorescent tags, the possibility of deterministic chaos is swapped by white noise due to molecular fluctuations. So, concluding, we have reviewed the basic motifs in many vital phenomena. These oscillations are of a huge importance for the correct performance of different vital and physiological pathways. We have also shown the basic design principles of biochemical oscillators, concluding that all are built up around some sort of negative feedback that is used to achieve stable steady states, which is translated into physiological homeostasis. Thank you very much for listening.